Hi, everybody. We're going to be looking at Unit 1, Lesson 1, Variables, Terms, and Expressions. So I'm going to go ahead and read this first paragraph here and kind of talk about what we're going to be doing today. Mathematics has developed a language all to itself to clarify concepts and remove ambiguity from the analysis of problems. To achieve this, though, we must agree on basic definitions so that we can all speak the same language. So we start this course in Algebra 2 with some review of concepts that you saw in Algebra 1. So here are some basic definitions that we'll be using. We have variable, terms, and expressions. A variable is a quantity that is represented by a letter or symbol that is unknown, unspecified, or can change within the context of a problem. So all of those things match the definition of a variable. For our purposes, and what we're going to be talking about today, we're mostly going to be focusing on letters. We'll get into these other definitions of variables as we come forward. So a lot of times when we're dealing with variables, we're going to be dealing with letters. X is a very, very common one. We may also have Y or some other letter or symbol. Terms, that's the next vocabulary term here. A term in mathematics is a single number or combination of numbers and variables using exclusively multiplication or division. Terms that are alike can be combined with addition or subtraction. So a term is, I like to think about them as sort of the words of math. So a variable is like a letter or a piece. A term is like a word, and an expression is going to be kind of like a sentence. So a term would be something like 3x. You have this number 3, this variable x, they're put together. Technically, there is multiplication happening in between these things. It's 3 times x, but we put them all together and this makes a term. They can be shorter even than this. They could just be a single number, 1, 2, 3, -6, right? They could just be a plain number. They can be much more complicated. They could have exponents as well. So you could have something like 4, y to the third. This is another example of a term. Everything here is multiplied together. They could also include division, usually in the form of a fraction. So we could have something like 5x squared over y. This is also just a singular term. The only operations that are happening here are multiplication and division. Again, division coming in the form of a fraction. And then our last thing here is an expression. An expression is a set of terms that are put together using addition and subtraction. So let's just make something up. 5x squared minus 10x plus 3. Here is a expression. In this expression, we have 1, 2, 3 separate terms and some variables in there as well. We have some x's, but this here is an expression. All right, let's go ahead and talk about expressions using this expression right down here. We have 2x to the second power plus 3x minus 7. So what can we do this? What can we do with this? Well, one thing we can do is observe it, right? What do we notice about it? What do we notice about it? Well, there are a few different things that we can notice about expressions. One we talked about is the number of terms. We could talk about the variables that are involved in our expression. We could talk about the different mathematical operations that we see, right? Here we have some addition, some subtraction, some multiplication, an exponent. We have a lot of different operations that are taking place. So those are some observations that we can make about it. Another thing that we can do is we can evaluate. And evaluate means to take a number or sometimes even another expression and substitute those numbers or expressions in place of the variable. Let's take a look at what that actually looks like real quick. Let's say we wanted to evaluate this expression for, we'll say evaluate for x equals, and then we pick a number. Let's just say x equals 1. 1 is an easy one to work with. So what that means is everywhere there's an x, we're going to replace it. We're going to substitute. That's the mathematical term with a 1. The way that I like to do this is I like to rewrite my expression But instead of the variable that I'm substituting for, I'm going to leave some big open parentheses. And inside of those parentheses, I'm going to go ahead and put the number that we're going to put in place of it, that we're going to substitute. So instead of the x, we're going to be putting a 1 in both of these spots. From here, we have to remember how to evaluate a mathematical expression like this when it just involves numbers. So there's a really important idea here called the order of operations. So the order of operations are parentheses first, then exponents, then multiplication and division, and finally addition and subtraction. So when we say parentheses, we mean any sort of mathematical operations that are taking place inside of parentheses. There may be parentheses involved in our problem, but we don't actually have anything happening inside of them. So we may not always do this step. Exponents, if there happen to be any exponents, that's what would come next. Then multiplication or division, we just read those left to right, whichever comes first. You don't always do multiplication first before division. And then addition and subtraction, again, those are grouped just like multiplication and division because we just do them left to right, whichever comes first. So let's evaluate this one. We do have some parentheses here, but there's nothing happening on the inside. There's just a number in there. So there's not actually any parentheses step in this particular problem, even though there are parentheses. Exponents. There is an exponent here. So there is something that we'll be doing here. We'll be evaluating this exponent first. So 1 to the second power means 1 times 1, 2 of them. Well, that's just 1. 1 times 1 is 1. And then I'll rewrite everything else here. I'm going to go through this a little bit faster because we are gonna do more of this in the future. Then we have 2 times 1. Oh, sorry. What's next? What's the next step here? The next thing is any multiplication or division that we see. And here we have multiplication. Anytime we have a number in parentheses next to each other, that's, again, another way for us to represent multiplication. So we need to multiply these things. When you're doing this evaluation, you can often do more than one step at a time, but you do need to be very careful. You want to make sure that these steps don't sort of depend on each other and kind of interfere. So you have to make sure that they're sort of separate. And in this case, these are separate from each other. We're going to multiply them together, and then eventually we'll add those results. That's what that addition is having us do here. So we have the multiplication taking place. 2 times 1 is 2, plus 3 times 1 is 3, minus 7. And then finally, we've reached the step of addition and subtraction, which is all we have left. We just do this from the left to the right, just like you read a page. 2 plus 3 is 5. 5 minus 7 is -2. So overall, we get a final answer of -2. So this is all evaluating. We substituted a number in place of our variable to evaluate the expression. You can evaluate it. You can evaluate expressions for any number that you want. I'm going to go ahead and put that word in there, substitute. That's what's happening here. Substitute for the variable or variables, depending on how many there are. And then finally, the last thing that you can do with an expression is you can simplify an expression. We're going to be doing this a lot, simplifying expressions. There are many different things that you can do that are considered simplifying. So you can do something that's called combine like terms. So any terms that have the same variable and same exponents, you can add those together or subtract those from each other, depending on what we have in the problem. You can use what's called the distributive property, where we have a number outside of parentheses and we distribute that number in using multiplication. We can like add fractions together or simplify fractions. So we can combine fractions or simplify. There are a lot of different things that fall in this category of simplifying an expression. These are just a few of the things that are fairly common. All right. We'll go ahead and move down and answer some questions about this expression below. So I'm going to go ahead and do that. All right, so we're considering the same expression there, and that is 2x squared plus 3x minus 7. So we have 3 parts. We're going to make an observation about it, we're going to evaluate it, and then we're going to do some simplifying. So observe. How many terms does this expression contain? Well, each term of an expression is separated using addition or subtraction. So something that you can do here is you could just draw some lines through any addition or subtraction here and see how many parts of this equation we have. So I went ahead and drew some lines. So hopefully we can see that this expression has 3 terms. There's one term, which is 2x to the second power. There's a second term here, which is 3x. And then there is a third term here, which is 7 or minus 7, negative 7. However we want to think about that. There's some nuance there. Anyway, there are 3 terms. That's not the only observations that we can make about this. We could talk about more things like the variable in this problem is an x. There are a lot of different operations, multiplication, addition, subtraction, exponents, and so on. But that's what we're going to do for right now. All right, next is evaluate. So we're going to evaluate this expression for x equals negative 3. So again, I'm going to rewrite my expression, but I'm going to use open parentheses anywhere my variables were. So 2 parentheses, that's where that x was, to the second power, plus 3x, again, open parentheses there, minus 7. So this is the same expression that we used before, so we should be pretty familiar with it. We're going to evaluate it for x equals negative 3. So where these x's were, we have our open parentheses, we're going to be putting in negative 3. And now we need to follow the order of operations, parentheses, exponents, multiply, divide, add, and subtract. Now, I spoke a little bit before about parentheses. Parentheses are not always parentheses. There are other things that can be considered parentheses. So some people actually call this category grouping, any grouping of operations. We'll get more into that in the future when we look at some more complicated expressions, but there are other ways to group that are not necessarily just parentheses. Anyway, we don't have any parentheses in this problem that we need to use because inside of these parentheses is just a single number. There's nothing to do with it. It's just a single number. But we do have some exponents, right? Or at least one exponent right here. So we're going to evaluate that. We're going to do 3 to the second power. Sorry, negative 3 to the second power, which means we do negative 3 times negative 3, 2 times, which is 9. A negative times a negative is positive. So we end up with 2 times 9 plus 3 times negative 3 minus 7. So we are done with exponents. Now we need to do multiplication and division. Here we have some multiplication. And here we also have some multiplication. We can actually do both of these at the same time. You got to be careful with this, but oftentimes you can do more than one thing in a single step, but do be careful with that. 2 times 9 is 18. 3 times negative 3 is negative 9 minus 7. And then finally, we only have addition and subtraction left. We have a couple of them. We have addition and subtraction. Hopefully we remember how to handle positives and negative numbers, but we'll kind of talk about it here too. Our first operation is this addition. We have 8 plus negative 9. So we're 18 plus negative 9. Another way to think about this, instead of adding a negative number, some people like to just think about this as the same thing as 18 minus 9. Either way, we get a result of positive 9 from this, and then subtract 7, minus 7. So our final operation is a subtraction. 9 minus 7 is 2. And so the result of this evaluation, we get 2, just a single number there. We're going to do this more, so I'm not going to stick with this too much. All right. And then finally, we're going to do a little simplifying. This expression itself actually doesn't have any simplifying that can be done. But if we want to go ahead and take this expression and add it with another expression, we can do some simplifying. So we are going to take the sum of this original expression we are dealing with and we're going to add on this other one, 5x squared minus 12x plus 2. We're going to go ahead and add those together. That's what the word sum means. A sum is a result of addition. So we have 2x squared plus 3x minus 7 plus our other expression here, 5x squared minus 12x plus 2. All right. Now, technically, we're taking this expression here, and we're taking this expression here, and we're adding them together. So we might want to think about them in terms of being in parentheses. That actually won't make a difference with addition, but if we were doing subtraction, it would actually make a difference. So, all right, so when you are adding things together, you need to be careful to only add like terms. So when I say like terms, I mean that they have the same variables. So same variables and the same exponents. So we add x's with x's, x squareds with other x squareds, and so on. All right. Let's go ahead and identify some like terms here. So we have this term 2x to the second power. That is going to be a like term with the other, with a term in the other expression, 5x to the second power. They have the same variable and the same exponents, right? Both have an exponent of 2. And we can add those together. We're doing 2x squared plus 5x squared. We add those together, we get 7. 7x squared. Notice the thing that changes is actually the number in front. We call that the coefficient. When you're adding, the coefficient changes. The variable and the exponent should not change. That's only going to happen when you multiply. When you multiply, you can mess with the variables, but when you're adding or subtracting, those should remain the same. Okay, let's go ahead and move forward with this. Keep identifying our like terms. We have 3x, positive 3x. We have another x term here, minus 12x. I'm going to think about that as a negative. So we have positive 3x plus negative 12x. 3 plus negative 12 is actually negative 9. So we're going to get negative 9x. That's going to be the result of adding those two terms together. The last one, let's go with blue here. We have a constant term, just a plain number here. We have negative 7. And then in this other expression, we have another constant as well, 2, positive 2. So we're adding those together. Negative 7 plus 2 is negative 5. So here is the result of our addition. This is the sum of those two expressions. 7x to the second power minus 9x minus 5. All right. And yeah, great. Let's go ahead and move forward here. I'm going to clear this and move to the next page. All right. So next thing we're going to talk about are called properties of the real numbers. So these are some rules or processes that can be followed when we're dealing with real numbers. Real numbers, hopefully we kind of have an idea of what this means is, but real numbers are positive numbers, negative numbers, fractions, terminating decimals, okay, they are irrational numbers. This is actually a mistake. They can be rational numbers or irrational numbers. An irrational number would be something like the square root of 2. That is a real number. It just can't be represented using a fraction, so we call it irrational. There is no fraction a over b that represents this number. That's not necessary for us to know, but that's what it means by an irrational number. Is you can't represent it as a fraction. We can represent a lot of numbers as fractions, like even whole numbers, right? Like 2 can be represented with a fraction in a lot of different ways, but a simple one is just 2 over 1. That's called a rational number. Anyway. All right, so these are the properties here. We have three properties that we're going to talk about right now. They're called the commutative property of addition and multiplication. That just simply means that you can change the order of these things, and we're good. It's the same. So for addition, let's just look at this really quickly. 2 plus 3, obviously that's 5. We know that's 5. But that's going to be the same thing if we do the addition in the other order, 3 plus 2. Doesn't matter. We can do 2 plus 3, 3 plus 2. We're going to get 5 no matter what. This also works for multiplication. The commutative property also works for multiplication. So let's just change this to multiply. 2 times 3 is 6. 3 times 2, also 6. Works for all numbers no matter what. Doesn't matter the order. Careful though, it does not work for subtraction or addition, right? Let's just quickly look at that. If you do 2 minus 3, well, that's -1. But if I switch this, 3 minus 2, that's 1. These are not the same thing. So the order of subtraction does matter. You can't just switch it around. Same thing for division. Let's do some other numbers that like actually divide. So 10 divided by 2 is 5. But if we do 2 divided by 10, we can represent that a couple different ways, but 1 would be 0.2 decimal. These are not the same thing. So the order that we perform division also matters. So this only works for addition and multiplication. And it's just, if you switch the order, you're allowed to do that with these two operations. All right, let's go ahead and take a look at the second property here. Second property is called the associative property of addition and multiplication. Association really means like getting together, right? So association is based on parentheses. You can change the place of parentheses or change the grouping when you're performing addition. So if you have, let's say, 3 things that are added together, 1 plus 2 plus 3, you can group these however you want. You can perform the addition in any order that you want. It's going to be the same. So let's just say if we had it grouped like this, 1 plus 2 is 3, plus 3 is 6, right? So we grouped it in this particular way and we got 6. But it's the same if we group it in another way as well. Let's say we move those parentheses. Instead of grouping the 1 and 2 together, we group the 2 and 3 together. So 2 plus 3 is 5, plus 1 is also 6. We get 6 no matter how we change the grouping here. And this works again for addition, not subtraction. I'm not going to show that, but it doesn't work for subtraction. It does also work for multiplication. Again, let's just say we have 3 things here. We'll do 2 times 3 times 4. 2 times 3 times 4. And we'll take a look at 2 different groupings here. So let's group these together. And let's do the same thing, but we'll group the 3 and the 4 instead. Okay, again, I'm grouping them using parentheses, which means I need to perform that operation first and then the other things. So 2 times 3 is 6, right? 6 times 4 is 24. So we get 24 with this one. 3 times 4 is 12. 12 times 2 is again 24. So it didn't matter what order I sort of did things, which way I grouped them, I got the same answer. Very, very useful property for performing multiplication of multiple numbers or addition of multiple numbers. You can sort of group them however you want. And then the last one is called the distributive property of multiplication and division across addition and subtraction. Sounds complicated, but basically what it says is if you have a number outside some parentheses that's multiplied in, you distribute that multiplication. You multiply it to both things. So you multiply that C times the A and the C times the B, and it goes across the addition, over the addition. It goes to all things on the inside there. Same is true for division. So if you're dividing something by a number like this, you can distribute that division to all parts. So that you have A divided by C and B divided by C. Both of these things are very, very useful. We'll run into the distributive property quite a bit. Always has to do with either distributing it in or the opposite. Sometimes you can distribute something out. That is a little more complicated, and there's actually another word for that that's commonly used when you kind of go backwards. It's called factoring, but we're still going to call that the distributive property, even when we go backwards with it. All right. I'm going to go ahead and clear this and kind of move down and take a look at this exercise here. We have exercise 2. So the procedure for simplifying this linear expression is shown below. So we're simplifying this. We're going to perform the distributive property, combine like terms, all that stuff. And what we're going to do is try to use these 3 properties to explain how we are able to do that. Which one of these allows us to do what we're doing. It can be a little bit tricky to try to decide what step we're looking at, so I'm going to try to make sure to point that out clearly here. All right, so here we go. We have our first one. We're going from this expression right here. So we're starting right here at the original expression, and we are going to that. We're moving to this thing, and we want to know, how did that happen? What is the difference? What do we see that took place? So hard to tell just by necessarily looking at this one. It might jump out to you, it might not, but I'll go ahead and point it out. What's happening here is the distributive property. These numbers on the outside are getting multiplied in. We're multiplying the 8 times 2x and the 8 times 3. That's distributing. And you can see that's what's happening right here and here. 8 times 2x, 8 times 3. And then the same thing is happening 5 times 3x and 5 times 1. So this is the distributive property. I'll write that out there. Distributive. Okay. Again, let's take a look at what's happening next here. Sorry. Okay, so we have the distributive property. Now we are going from here. A little bit hard to see what's going on. I want to know how we got to this step. So how did we go from this to here? Well, what's really different about it? Let's focus on what looks different here. And the thing that I notice are these parentheses. These parentheses were not there before. We grouped things in a new way. We used our parentheses to change groups. That is called the associative property. So anytime we're putting parentheses in to change the grouping, it's called the associative property. So that's what we're going to put in here. Technically of multiplication, is what's happening here is we're changing the order of our multiplication or the grouping of our multiplication. It wasn't changing addition there. Let's go ahead and take a look at our next step. So we're going from here, from this, which is pretty simple already. We're going from that into this. So let's take a look at what has changed, what is different. So you went 16x plus 24 plus 15x plus 5. And what we've done is we've changed the order of some things here. The 16x so hopefully you can see here that some of the terms have switched places. I guess it looks like these two here, the 24 and the 15x, looks like they've switched places. So if we're changing the order of terms, that is called the commutative property. So we have the commutative property. Let's go ahead and put that down there. Commutative. And this was technically of addition because we were adding these terms together and we changed the order of the addition. So commutative property of addition. All right. This next one is one of the trickier ones here. We are introducing some parentheses, which some might confuse with associative property, right? We associated things here when we introduced our parentheses, but actually a little bit more of a complicated things going on here. So what we're doing is we're taking a look at simply these two terms, 16x plus 15, and we are taking this x and I'm going to say undistributing it. So doing the reverse of distributing it, we're taking it away. The technical term here is we're actually doing something that's called factoring. We are factoring it out. That's the opposite of distributing, and we're putting it on the outside of these parentheses, right? If we were to redistribute this back in, right, we would be back where we were before. So we're doing sort of the distributive property, but in reverse. And the one term that we're going to use for that pretty commonly is called factoring. Anyway, so that is the distributive property. And then our last step, our last justification here, we've changed some grouping, right? We've just decided to group these two terms together, and that's it. We're doing something called the associative property again. This time it was the associative property of addition. And then we'll simplifying and we're done. This is very complicated. This whole process that we went through here, I'm hoping that you can sort of understand some of the things here and how these rules are being used. There are some extra steps here that while we are trying to go through and simplify expressions, we're not necessarily going to do them. But I do want to make sure that you can kind of see these things and see how these three properties are used in order to allow us to simplify these things. Let's actually take this expression here and let's try to simplify it on our own in a less complicated manner. We're going to take away some of these things and try to make it make a little more sense, a little more intuitively. So I'm going to actually just clear everything that I have and start at basically the beginning, but we have 8 times 2x plus 3 plus 5 times 3x plus 1. So here is our original expression. And I'm going to follow all of the same steps really, but I'm going to do hopefully a little bit of simplifying in this process. So obviously distribute. So distributing multiplication, we're doing 8 times 2x, 16x, 8 times 2 is 16. 8 times 3 is 24. There we go. We'll distribute again over here. We have 5 times 3x, that's 15x, 5 times 1. So again, we use the distributive property just like what happened in the other one. Now, the next thing that I would do here, I wouldn't necessarily look at this and think about needing to rearrange terms, although because we're allowed to change terms, that's why I can just sort of put things together even though they're not necessarily right next to each other. I would be looking for just simply combining like terms, right? What are my like terms? My x's and my x's, my plane numbers and my plane numbers, what are they? And they took an extra step here, right? They reordered things. They said 16x plus 15x plus 24 plus 5, right? They reordered terms, so they put the ones that were alike next to each other. We can sort of skip that. We don't necessarily have to do that. But anyway, let's go ahead and add these together. We get 31x plus 29. Now, again, the reason this actually works in this way, the reason that when we add them together, we actually just get 31x and the variable doesn't change, has to do with this step here of this factoring and everything that's going on. But I'm okay skipping over that justification necessarily when we're just going through the process of simplifying. Anyway, we got the same answer. All right, let's move on to our third and final page, I believe, here. So in these last steps, we were able to show that this expression could be simplified into a much simpler form, into 31x plus 29. And in doing so, we know that these expressions are actually what are called equivalent to each other, that for every value of x, they are equal. We can test this equivalency by evaluating the expressions for the same number and see if it works out. So what we're going to do is we're going to choose a simple number here. We can choose any number we want, some easy numbers, pick something small, something easy to work with. I'm going to go ahead and use 2. I could pick easier numbers, but I'm going to go ahead and go with 2. So I'm going to evaluate these for 2, which means everywhere there is an x, I'm going to put a 2. So there we go. Right here were my x's. I went ahead and placed a 2 in there using those open parentheses like we did in the past. So let me just kind of highlight that right here where the x's were. That's where I put those open parentheses. And then inside of the parentheses, I put in the number that we were told to use. So there we go. Now we need to evaluate this, being careful to follow our order of operations. In this case, there are parentheses. There are a lot of things to do inside of some of our parentheses, right? So if we look right here, there's a lot to do. There's a lot of mathematical operations that are happening inside of these parentheses. So we're going to do that first. When you are inside of the parentheses, you also have to follow order of operations inside there because there are multiple things happening. We have multiplication and addition going on, so we need to make sure to do those in the proper order. Anyway, 2 times 2 is 4, plus 3 is 7. So this ends up being 8 times 7. Same over here. 3 times 2 is 6, plus 1. It's actually 7 also. Convenient there. So we did everything that was inside the parentheses. And we got 7 for this one and also 7 for this one, right? And then we have multiplication. 8 times 7 is 56. And 5 times 7 is 35. And now we add these together and we come up with a final result of 91. So when we evaluate this expression for x equals 2, we get 91. Let's go ahead and evaluate this other expression for the same number for x equals 2. They should match. If these two expressions are indeed equivalent to each other, if we did all of our simplifying correctly, we should get the same answer. But let's make sure. So 31, no parentheses, this are open parentheses here, right? We're going to put a 2 inside of there, plus 29. All right, much easier, simpler expressions, some bigger numbers, but less to actually do here. We only have multiplication and addition. We got rid of a lot of stuff. Anyway, 31 times 2 is 62 plus 29. 62 plus 29 is also 91. Now, this is a way for us to test equivalency. If we have two expressions, we could test to see if they were equivalent by just plugging in numbers, same number into both. And if we get the same thing, that should lead us to believe that they might be equivalent. It is not a perfect solution. It could just be a coincidence, right? It could just be a coincidence that our expressions gave us the same value for this number. So if this is the only way you're deciding if two expressions are equivalent, that's being a little bit too simple. Let's look at something that we could do here. So let's look at this is a little bit of an aside, but let's examine two expressions which don't really look equivalent, x squared minus 1 and 2x minus 1. Let's go ahead and see. Let's try that same number. Let's try x equals 2 into these, see what happens. So 2 squared minus 1. 2 squared is 4. 4 minus 1 is 3. 2 times 2 minus 1, that's 4 minus 1, that's 3. Well, this simple test would tell me that these are equivalent, right? If I just kind of follow the steps from before, we might think that these two expressions are actually equal. But turns out it's just a coincidence. They work for this particular number, but if we try something else, they're not going to work. If you try, for example, the number 3, you'll find really quickly that they don't work. 3 squared minus 1 is 9, minus 1 is 8. You get 8 for this one. 3 times or sorry, 2 times 3 is 6. 6 minus 1 is 5. You got 8 for one, 5 for the other. And there you go. You see that they're actually not equivalent. Kind of interesting. Let's go ahead and clear this and look at this final thing here. So constructing arguments is a really important thing that we're going to be doing a lot. So we're going to be using mathematical vocabulary, complete sentences to explain our answers. So here are some good sentence starters. These expressions are equivalent because when I evaluated both for x equals, they result in the same simplified value. Or these expressions are not equivalent because when I evaluated both for x equals something, they result in different simplified values. These are nice sentence starters. This is what a good constructing arguments answer would look like if we were asked, explain how you know that these expressions are equivalent or not equivalent. Well, we evaluated both of these expressions for x equals 2, and we found that they resulted in the same simplified value, right? We got 91 for both of them. So this would be an excellent constructing arguments example with the additional provided work where we see what the expressions actually came out to be. If we found that they were not equivalent, you could see, oh, when we plugged in 2, we got different numbers. For example, in that previous problem that I was showing kind of the aside, when we substituted x equals 3, these two expressions were not equivalent. When we put in 3 here, we get 3 squared minus 1 is 9 minus 1, we get 8. And then for this one, we get 6 minus 1, which is 5. So when you plug in these are not equivalent expressions. So make sure you're thorough with these constructing arguments. We'll make sure in class we'll have plenty of time to practice these types of questions. And that's all for this first lesson. Make sure you get the homework done, and I'll see you guys later.